Okay, so last time we talked about position versus time plots, and based on the clicker responses, you guys had absolutely no problem grasping this. So we'll try something a little harder. And so now what I'm wanting you to pick is one of these plots, so these are position versus time. One of these plots represents an object which moves with a constant velocity from a certain point, stops for a period of time, and then returns back to the original point with a constant velocity. So which of these four graphs represents an object that's doing that? Wow, 112. Ah, great. Okay, so democracy seems to work this time at least. So indeed, the large majority of you indeed got exactly the right answer. Oops. Where's it going? No. Yeah, I don't know. It's the larger number of students seems to have made this thing a lot more sluggish than it's been in previous years. There we go. Okay, so the correct answer is indeed C. So we won't do the second part because a lot of you, a large majority of you got it right. So this one here, so why is that? Well, so here's our time, here's our position. So if we've got a constant velocity, remember, that's the gradient of the line. So you want something that's got a straight line. So the first part of the journey, if you're moving with a constant velocity, must be a straight line. So you can immediately rule out D, because that's a curved line, so it can't be D, but it could be A, B, or C. So that's the first part. The second thing says it's got to stop for a period of time, which means if it's stopped, it has zero velocity. Zero velocity means zero gradient, and zero gradient means a horizontal line. So you've got to have a horizontal line as the next section, and so that rules out A, because A does not have a horizontal line. So now we're down to B and C, and then the thing says it returns with a constant velocity. So there's two ways you can think about that. You can either think of it as, well, it's returning, so its position has got to go back to zero, which means it's got to end up back here on the x equals 0 axis if it's returning to where it started. So that's one way you can think about it. So you've got to have a line pointing down for that, which would rule out B. The other way you can think about it is if it's returning, it must have a velocity in the opposite direction to its initial velocity. Well, it started out with a positive gradient here. So you've got to end up with a negative gradient, an opposite sign gradient at the end. So you've got to have a line that slopes down. So either of those two arguments will point you to this, and then of course it gives you the answer that's C. So either of those two ways of thinking about it, but you end up with C. Okay, so this is one that I got a couple of emails about, but people didn't actually comment too much about on the quiz. So what we've been talking about so far has been average velocity, so the mean velocity over a period of time. However, that's not necessarily useful, right? You can change the velocity of something. You know, if you set off in a car, it starts at rest and it accelerates. So you don't necessarily want to know the mean velocity over that period of time. You want to know the instantaneous velocity, right? So you want to know at any one instance of time how fast is an object moving. So, you know, if you drop an object, you get the similar sort of thing. If you're dropping an object, it's accelerating, the velocity is continuously increasing. So what we've got to calculate is we've got to figure out how to calculate a velocity at a particular instant in time. And this is where the dreaded word calculus comes in. We can't do it any other way. In fact, Isaac Newton, who was one of the guys who developed calculus specifically to be able to describe this, right? So in other words, the physics actually drove the development of the maths, and this is actually not an uncommon thing. If you look at string theory now, which is this sort of theory they've got for it explains everything, as they say, which is maybe a little bit of an exaggeration, but pretty much everything. Of course, we don't know that it actually works. But the theory that they've got is so amazingly complicated from a mathematical point of view that it's actually driving the development of maths. And there are mathematicians, in fact, in the maths department here who work on string theory from the mathematical side, developing new mathematical techniques and tools to be able to describe the theory that the physicists came up with. So, you know, that's an example where physics is actually driving the development of new maths to try and explain the concepts that they're developing. So this was the case here. Obviously, maths here a little bit easier than string theory, but you know, this was 400 years ago. The same thing was happening. Isaac Newton was pushing the development of maths in order to be able to explain the physics. So what we're going to do is we're going to take an average velocity for a certain period of time. So if I've got an object and it's moving between 2 points, so I've got something here, and it's moving between 2 points, and it takes a time delta t to move from this point between these 2 points, right? And this is a distance, a displacement between the points of delta x, right? So we've got an object, it moves between 2 points that are separated by a distance delta x, and it takes a time delta t to move between those 2 points. So we can calculate the average velocity of the particle, or whatever it is, that's moving between those 2 points, and we get the average, so that's the velocity, the average velocity will be equal to, just as we've done before, delta x divided by delta t. Right? So nothing different than what you've already seen. Only now I'm using lowercase delta. So where I used capital delta, I meant a big change. When I use lowercase delta, I mean a small change. We've got a small change in time and a small change in position. Oops. Shall I zoom in a bit then? Okay, make it a bit clearer. Okay, so we've got a small delta t, small delta x. Average velocity during that period of time is delta x divided by delta t. But that's still a period of time. That's still not a useful thing. We want to know the velocity of an object at an exact point in time. So what I want to do is I want to make these points closer together. So I can do it from here to here, and I can have my object now moving there. And I've now got the average velocity over a smaller point in time, but it's still over a distance in time. What I want is I want this to disappear. So I want to calculate the velocity in the limit that my time period goes to 0. So I'm calculating an average velocity in the limit that the time period goes to 0. So if I... No, it wasn't loud enough, I think, to be a real fire alarm. So the average velocity here, so what I've got now is I've got a velocity, but I've made the points shift so close together that instead of over a period of time, I'm taking the limit as that period of time disappears and goes to 0, which if you're familiar with calculus is exactly what you do in calculus. So the velocity at a point, at an instance in time, so a point in time if you like, is the limit as this time period delta t goes to 0 of delta x divided by delta t, right? And this is what we write as dx by dt, where x, of course, is a vector. So we've got dx by dt, which is the differential of the position with respect to time. So all I'm doing is I'm taking the limit as this time period goes to 0, and so we calculate the velocity at a single instant in time. Now, I think the emails I got were sort of, well, hang on a minute, though, you're taking a limit as delta t goes to 0. But we are taking the end point of that limit. We're taking the limit where it has actually gone to 0. Now, maybe this method here, when we're calculating it, doesn't perhaps illustrate it. Lots of you have heard about kinetic energy, right? Who has not heard of kinetic energy? Excellent, right. So you've all done kinetic energy at high school. So the other way you can think about this is the object has got a kinetic energy, and if I told you the mass of the object and the kinetic energy, you can calculate its velocity. And in that calculation, you've taken no limits, right? There's no limits involved as delta t goes to 0. When we're doing it via mechanics like this, via kinematics, then yes, you do have to worry about taking a limit as delta t goes to 0, but you are actually calculating a property of the object, and it's a property that the object possesses, right? So the object possesses a velocity at a particular instant in time, right? And if you think about it from the energy point of view, it becomes a lot clearer because there's no limits involved. But here we're doing it from sort of first principles via kinematics. So hopefully that explains why the answer to one of the questions was that the instant in time really is a point, an absolute 0 delta t. It's a particular value of time. It's a point in time, not some tiny, tiny interval, right? It's as the tiny, tiny interval goes to 0. So any questions on that? Yeah.
When you take the limit for time, you said it's going to 0, but could you choose like 5 seconds or something like that?
But then you wouldn't have the instantaneous velocity. You'd have the average velocity over 5 seconds. Okay, so what you need is you need to know how the position changes with time, right? Because you're interested in the rate of change of position. So you have to know how the position changes as a function of time in order to be able to calculate the velocity at any instant in time. So you can't just concentrate, you can't say, well, I know what the velocity is, I know what the position is at 5 seconds, and then I just calculate it at 5 seconds. You have to, I mean, when you're doing the differentiation like this, you'll end up with a formula that depends on time, or could be constant, but you'll end up with either a constant or something that depends on time, because you've got to know how the position varies with time. You can then evaluate that at t equals 5 seconds, right? But you have to know how the position varies over time. What this will give you then is a formula that shows how the velocity varies with time. And then you can put t equals 5 seconds into that. But you can't do it just saying, I want to know exactly what it is at 5 seconds. Because you've got to know more information than that to be able to calculate what it is at 5 seconds. Okay. Any other questions? Okay, so again, if you're unhappy with calculus, there's a lesson on the website. You probably won't be doing it in Maths 113 until about half term, but you know, we've got to deal with it now, right at the start, because it's one of the fundamentals of kinematics, and there's no way we can do kinematics without doing a little bit of calculus. So unfortunately, I know that's not ideal in terms of the ordering, but that's why we have Maths 31 as strongly recommended for the course. So this is how you calculate the instantaneous velocity. You differentiate the position with respect to time. Okay, so the other way we can look at that was sort of the simple picture. The other way we can look at it is we can look at it from a graphical point of view as what's going on with our position versus time plots. So if we've got a position versus time plot here, and now we've got some curved line. That's how the object changes its position with time. And we say, well, okay, what's the velocity at this point here? Well, what we can do is we could take a period of time here, and we'll call that delta t, and we'll take, and that corresponds to a change in the displacement of delta x. And so the gradient of this line here gives you the average velocity during that period of time around this point where we actually want to know the velocity. So we have here that the gradient is equal to delta x over delta t. That's better. So we've got delta x over delta t. Well, of course, that's, as you can see here, there's a bit of a gap here. This is not exactly what the object's doing. So we can shrink down that gap, right? And if we make it between here and here, and this is the point we wanted about, there's still going to be some slight difference between the line. So this will be delta x now, this will be delta t. There's still going to be some slight difference here. It's not exactly going to match the line. Within the resolution of the thickness of the pen stroke, you probably can't see that, but you can hopefully understand that there will be a slight difference even if we shrink the thing down. And what we want to do again, just as we did here, is we're taking the limit as this goes to 0. So we want to take the limit as delta t goes to 0, and when we do that, we're going to end up with this triangle shrinking, and the hypotenuse of that triangle will then precisely match the gradient of the line at that point. So what you end up with is, if this is the point you're wanting to calculate the velocity at, you end up with a triangle, a tiny triangle, so that's it's microscopic, but the hypotenuse of the triangle is parallel to the gradient of the curve. And so the other way we can think about this is, again, just like we did for the constant velocities, where we looked at the gradient of the curve. It's the same thing here. So on a position versus time plot, we're calculating the differential calculates the gradient of the curve at a particular point, and the gradient of the curve is the velocity of the object at that point in time. Right? So it's the same concept we had before for the straight line graphs, but now we're doing it with a curve, and at every point on that curve, the gradient of the curve tells you the velocity. Any questions about that, right? That's the graphical way of looking at it. You're just calculating the gradient of the curve. Okay, good. Okay, so next question. Which of these curves represents an increasing velocity? Okay, stop. Wow. Okay, so this is definitely an excellent one to turn to your neighbor and discuss which you think the right answer is, because we've got a three-way tie between B, C, and D. Okay, so let's see if we can break the three-way tie. So have another go. Okay, so let's see what we've got. Well, we've split the three-way tie. We're getting there. So one more time, we should be down to one answer. Okay, so I'll give you a bit of a hint how to think about this, right? So if you're looking at these plots here, right, what you're interested in is a change in the velocity, right? So rather than worry about how it's continuously changing, so obviously you've all ruled out A, so that's good. So when you're looking at B and D, was it B and D? Yeah, B and D that were the two favorites. What you want to look at is you want to look at the velocity at the start and the velocity at the end. You want to decide whether it's positive or negative and how positive or negative it is. Is it very negative, very positive, slightly negative? And if you think about that and the change involved, you should be able to figure out then whether the velocity has increased or decreased. So that's the way you should be thinking about it, looking at the velocity at the start and the end, deciding whether it's positive or negative and how positive or how negative it is. So we'll have one more discussion session, and then after that, I promise you I will tell you the answer. So turn to your neighbor and try and convince them that you've got the right answer. Okay, so let's have a final vote before we find the answer. So 30 seconds to cast your votes. Okay, here we go. Come on, show us. Whoa. So we didn't resolve anything. Okay. Okay, so I will show you the answer and I will tell you why it's the right answer. And some of you may want to kill me when I show you. So B is the right answer. So now, of course, you want to know why is B the right answer? Okay, so if we look, let's start with well, we'll do both of them side by side, right? So B was this, and D, sorry, was this. Okay, so this was B, and this was D. So in the case of D, if we look at the start velocity here, right, we look at the gradient there, and it's a shallow gradient, but it's negative, right? So you have a small negative. At the end of D here, you have a steep slope, which is also negative, so you have a large negative number. So if we go to B, we look at the gradient at the start here. You've got a steep slope, and it's negative, so you start with a large negative gradient, and you end up with a very shallow slope, but still negative, so you have a small negative gradient. So since the gradient is the velocity, in B, we are going from a large negative number to a small negative number for the velocity. And in D, we are going from a small negative number to a large negative number. So if you want to call the small negative number, say, -2, and the large one -10, I hope you all agree that -2 is an increase over -10, right? You are adding something to -10 to increase the velocity. So here we're going from -10, say, to -2, so you've increased the velocity by 8 meters per second. Here you'd be going from -2 to -10, so you would be decreasing the velocity by 8 meters per second, because velocity is a vector, and therefore the direction of the vector is important. If I was asking about speed, then both answers would be correct, right? But I wasn't asking about speed, I was asking about velocity. And only one of those shows an increase in velocity from a large negative velocity to a small negative velocity, right? So hopefully that explains it, right? With velocity, you have to worry about the direction. It's not speed. You can't just ignore the minus sign in front of it. You have to worry about it as you do for all vectors. So any questions on that? Yeah. Oh, sorry, no, that's right, you're wrong. I misspoke, sorry, you're right. Yes, sorry, B, if you were talking about speed, you're right, sorry. If you're talking about speed, B would be wrong. I think it's D, yes, yeah. In fact, if you're talking about speed, D would be the only right answer. You're right, sorry, I misspoke. Any other questions? Good, okay. So that was a challenging clicker question. Yeah. Who? Oh, there. Sorry.
Can you explain how to get like large negatives or small negatives, like a slope? Can you explain how to get it, or to get them from the distance?
You mean why is this a negative slope?
Why is it large? Yes.
Oh, because it's steep, right? The steeper the slope, the larger the value of the gradient is, right? And if it's sloping that way, it's a negative gradient, and if it's sloping the other way, it's a positive gradient. It all comes down to, right, the fact that if you've got a slope here and you're taking, delta t, delta x, here delta x is negative, right? And so that gives you a negative delta x divided by delta t means a negative slope, and the larger delta x is, the steeper that slope's going to become. Yeah. Okay, any other questions before we move on? Good. Oh, no, sorry, there. Yeah, wave your hands around, because with this many of you, it's difficult to spot who's got their hand up.
I'm still not sure why D is the wrong answer, because if, let's say that it's a position time curve for a plane, one is landing and one is crashing,
Sorry? B would be the landing one, and D would be the crashing one, yeah. No, oh yes. Well, I'll tell you what, we'll do an experiment. No, I'll sit on plane B. No. We'll see who crashes, yeah. So if you've got a large negative velocity, if you're counting upwards as positive, the last thing you want to have, if we're talking vertical velocity here, oh, are you talking vertical, are you talking horizontal? Well, in fact, either one, right? Either one, it doesn't matter, right? But let's say this represents vertical position, right? You do not want to be landing on a plane that's increasingly diving more and more steeply into the ground, right? That's yeah, because your velocity here is getting larger in magnitude and more negative, which means you're falling down more rapidly. Pardon?
So it's relative to which way you're calling, like positive.
Well, yeah, I mean, if you're saying downwards is positive, then neither of these would be a plane landing. They'd both be a plane taking off, right? So if you're talking about planes landing, if you're meaning this to be the vertical velocity, right, then you want the vertical velocity of the plane as it comes into the runway to be small, right? It'll never go to zero, because if it goes to zero, you're not going to land. Right? But in fact, this in fact this may well in fact be a good profile for the vertical velocity of a plane that's coming into land. It comes in steeply, and then you level off as you get close to the runway, and you have a very small vertical, negative vertical velocity as you hit the runway. Yeah? If you've got more questions, come and ask me afterwards if I haven't convinced you. Yeah? Sorry, can you speak up, sorry?
What?
Can you speak up? I missed the start.
I can see how both the and D are correct, because the question doesn't specify which direction you're increasing your velocity in. Because like in, like velocity is a vector quantity, right? Yeah. So on D, the velocity is increasing in a positive direction, as where D is increasing in a negative direction.
Yeah, okay, but okay, just hold it there, right? You're saying increasing in a negative direction. That's decreasing, right? I mean, decreasing means to get smaller, right? A minus 10 is smaller than minus 2. You're getting confused between magnitude of the velocity, and in that case, the minus and positive sign doesn't matter, versus the actual number for the velocity, right? So if I've defined, I mean, you're right, it's somewhat arbitrary. I could have defined the positive direction in a different direction. You know, if I'd have flipped the direction I'd call positive, then you indeed would be correct, and you would, because all the negative velocities will become positive. But when you've chosen a direction for positive, then you still have an increasing velocity if you go from minus 2 to from minus 10 to minus 2. It's an increase, right? When we talk about accelerations, it may become a bit more obvious, because in that case, you'll have an acceleration in a positive direction. Right, if you're going from minus 10 to minus 2. Right? It's increasing means becoming larger, and minus 2 is larger than minus 10. Okay, so we'll move on to acceleration. If you've still got questions about that, then come and see me. The TA's got office hours from 12 till 2 today. Remember, they got shifted slightly because of the Theoretical Physics Institute seminar. But by all means, come and grab hold of me at the end, or well, in my office afterwards, or grab hold of the TA, right? It's fine to ask questions, but we need to move on a little bit, unfortunately, in the lecture. So now we're talking about instantaneous velocities. We've clearly introduced the concept that a velocity can change. And so once we start having changes in velocity, we have to deal in kinematics how we're going to describe that. And we describe this with the acceleration. So the same way we did mean velocity, we're going to introduce a mean acceleration. And the mean acceleration is the change in the velocity divided by the time elapsed. So it's exactly the same thing we used for mean velocity, where we had change in position divided by time elapsed. But now we're talking about acceleration, which means change in velocity divided by time elapsed. This is the same sort of thing. There aren't many other examples other than acceleration. The only one I can think of is you can think of the acceleration as a change in the rate of inflation, right? So supposing, I don't know what it is at the moment, we've got about 2% rate of inflation here in Canada. So if on the news tonight, they announce that the rate of inflation has increased by 1%, that does not mean that prices have gone up by 1%. It means that the rate of change of prices has increased by 1%, right? So that increase in 1% in the rate of inflation is the same thing for sort of prices in the shops as acceleration is for position of an object. It's not the rate of increase in position or rate of change of position in the object, it's the rate of change of the velocity, which itself is the rate of change of position in the object. So it's a little bit of a complicated concept to get around. I mean, I'm sure you've encountered this before, but you do need to remember that it's not the same as the rate of change of position. It's the change in the velocity, not the rate of change of position. Okay, so consider a Formula One racing car setting off from the grid and moving in a straight line. We go from t equals 0 to 10 seconds, 0 initial velocity to 67 meters per second. What is the average acceleration after over this period? So the mean acceleration over this period. Okay. Brilliant. Okay, so I only got 9 of you with my trick. So the correct answer is indeed, if this thing will ever show it, no. No! You have to wait for it. It seems to be rather sluggish. So, no, I'm afraid B is the right answer here. So the little trick I was playing here was that meters per second is not the units of acceleration, right? We've got a rate of change, we've got a change in velocity divided by a change in time. So we've got acceleration, or the mean acceleration is delta V over delta t. This is in meters per second to the -1. This is in seconds, so this gives you meters per second divided by seconds is meters per second squared, right? So the right answer was B, because the units are meters per second squared. So that was a little trick there. So just as we did for position versus time, and we use the gradient there to calculate the velocity, we can also do plots of velocity versus time. So here, for example, you're seeing an object that's got a linearly increasing velocity. So an example of that is just dropping something. You get a nice constant linearly increasing velocity if you define downwards as positive. And so if we consider the gradient of this line, we have, between 2 points, we have a change in the velocity, and that corresponds to a change in time. It takes a time to change that velocity. So the gradient of this line is the change in the velocity divided by the change in time. So that's how we get the gradient of a velocity versus time plot tells you the acceleration. Okay, so next one. Which of these plots represents a negative acceleration? Right? So which of these is a negative acceleration? Okay, so we'll stop now. Excellent. So, oops, come back. So I only got 4 of you this time with my little trap. So the correct answer is indeed D, as most of you got. So so here at D we have velocity versus time, negative gradient. It's constant gradient, so we've got a constant negative velocity, and that was indeed the right answer. So my trick here is you've got a constant negative line, but the y-axis here is position, not velocity, right? So always look at the labels on your axes, and when you're drawing your own plots, which you may be asked to do in exams, always make sure you label the axes so it's clear what you're actually drawing, right? Because the labeling of the axes changes the interpretation of the graph. This is in fact a zero acceleration, right? Because it's a constant velocity, no change there's no change in velocity, so no acceleration. Okay, so if we're looking at one of these velocity time plots, we can use the gradient, and the gradient will tell us the acceleration. But the other thing we can do with these plots is we can look at the area under the plot. So if we have a graph that looks like this, we've got a nice straight velocity, so velocity versus time here. And the question we might want to ask is, how far has the object traveled? So what we're going to do is we're going to look at the area under this graph. So we can split this area into two parts. We've got a nice rectangle here, so this is the initial velocity, and this is the final velocity, v. And we've got t naught, we'll just call it delta t here. Right? Then the area of the rectangle, the total area here, A, is equal to the area of the rectangle, that's v naught delta t, plus the area of this triangle. And the area of a triangle, as I hope you know, is half the length times the perpendicular, half the base times the perpendicular height. Well, we've got a right angle triangle, so that makes it nice and easy. It's a half of the base, which is delta t, and the perpendicular height. Well, the perpendicular height is v minus v naught times delta t. Well, if we expand this out, then we've got v naught minus a half v naught. So we've got a half v naught delta t plus a half v delta t. We can factorize that, and we end up with a half v naught plus v times delta t. Well, v naught is the initial velocity, v is the final velocity, and if we add those two together and take a half, that gives us the average velocity. So this quantity here is just the mean velocity, right? And we're multiplying that by delta t. Well, the mean velocity, we already know that we've defined the mean velocity as the change in position divided by the change in time. So if I put this in here, we have the area is equal to delta x over delta t times delta t. Well, I cancel the delta t's, and that tells me that the area under this plot here, so what we end up with is the result we get is that the area is equal to the displacement. So if you take 2 points in time and you calculate the area under the velocity versus time plot, then that will give you the displacement that the object makes in that period of time. So this, although we've calculated it for a nice straight line, what we'll do next time when we start talking about instantaneous accelerations is we'll mention integration and show that you can do that for any shape of curve, not just for straight lines. So I'll see you all on Monday, and if you have questions, come and see me.